Hi everyone. Lesson 4.4 is going to build on what we talked about with normal distributions in our last lesson. But in this lesson, we're going to talk about confidence intervals. Okay? So remember, when we had a normal distribution, we used what were called z-scores to figure out the percentage of a sample that should fall within a certain range. Okay? One example we had was life of tires. So, we could say what percentage of our sample should last 90,000 kilometers in terms of life. Confidence intervals actually build on this. So they use the data we have, the number of data points we have, the mean and the standard deviation, to determine where a certain percentage of samples, and usually it's the upper levels, so 90%, 95%, or 99%, what range would allow that quantity of samples to fall within it. So once you find a confidence interval using a set of data, you can use that confidence interval to estimate future sets of data. So whether it's future manufacturing runs, experiments you're doing, testing on machined parts or on concrete, etc. So examples of this, like I said, would be if I want to determine the accuracy of a machine component, okay, let's say plus or minus a certain amount, let's say 0.001 millimeters, or to 1/10,000th, okay, of a millimeter, something like that. Or if you had a group of concrete samples and you wanted to determine the confidence interval that they would cure to within a certain strength level. Okay, all of those are items that we can use confidence intervals for. Okay. So in the basic form, a confidence interval relies on you calculating an error. Okay, so you have a mean value that you want to obtain, and you have an error that you can be within, plus or minus that mean, and that you can have to within a certain confidence limit. Okay, so 90, 95%, or 99% are common themes that you use. So basically what we're looking at here is our form is we have our mean, which is x bar, plus or minus our margin of error e. And we'll get in the next slide our formula in how to calculate that error. But I just want to explain to you what that means. So here we have a normal distribution. And if you remember, the normal distribution here is showing that the mean, right at the center, okay, is 0. And if you remember, it was symmetric on either side, okay? So on the left-hand side, made up 50% of the samples, and on the right-hand side, it made up 50% of the samples. So when we're finding a confidence interval, let's say we're finding 90%, what we're trying to determine is what actual values, okay, will be within 45% less and 45% more, okay, than the mean value, or 45% of values will fall within each side of it, right? Because remember, it's symmetric across the mean. So this light blue part here that I'm now shading in red, those would be our components, or our pieces that don't fall within our confidence interval, okay? So you might think, as an example, if you have a 90% confidence interval, okay, what range can I have so that 90 out of 100 samples that I have meet that criteria? And we're going to look at how different values affect a confidence interval, and because of that, why it's different than just looking at a plain normal distribution. Okay. So remember, we had our mean plus or minus an error. Our error takes into account 3 factors. It takes into account our z-score, our standard deviation, sigma, and lastly, and the most intriguing piece, in my opinion, is the number of samples. Okay, so the error takes into account all three of these variables. Now, looking here, our first term, our z-score, and it has alpha divided by 2. The reason for that is, remember, looking at a normal distribution, it's symmetric on either side of the mean. So your error on one side of the mean is just half, okay? And the other half is on the other side. And you remember when I calculate a z-score, you had a standard deviation. What it was calculating was a z-score for only half of the mean. So that's why this is z at alpha divided by 2, okay? Where alpha is actually the overall error percentage, okay? Or how many samples are not going to fall within the confidence interval. So for example here, if we have a confidence interval of 90%, that means 10% or 0.10 will not fall within the mean. So alpha here would actually be 0.10. And the alpha divided by 2 would be 0.05. Okay? I'm not expecting you to have to calculate these. I'm just showing you what they mean. And with that, if you were to look it up on a z-score, you would get your z-score for that of 1.645. And this table for these three specific confidence intervals will be provided to you for your test. At 95%, that means our alpha value is 0.05. So half of that would be 0.025. And that equates to a z-score of approximately 2. It's 1.96. If we look at 99%, our value for alpha would be 0.001. Okay, or sorry, 0.01, not 001. So half of that would be 0.005, and our corresponding z-score would be 2.575. That value, so whatever I tell you we have a confidence interval for, that z-score you substitute in here. So one thing I want to point out here, and we'll get into more of this in a couple slides, as you increase your confidence interval, your z-score increases, right? Because it now has to cover additional data. So as this value increases, your overall error will increase. Or in other words, your tolerance plus or minus your mean will increase. And that makes sense, right? Because it has to cover more data. 90% of data versus 95% of data versus 99% of data. Okay? The second variable is your standard deviation. And your standard deviation, if you remember, is looking at how closely distributed your data is from your mean. So the smaller your standard deviation, it means that your normal distribution here, maybe you'll look something like this, and it means the smaller your error. So if your standard deviation is a really tight number, it means your error can therefore be smaller, and your tolerances are higher, meaning that your whatever process you're using, whether it's curing concrete or machining components, is very good. If your standard deviation is high, that means your curve is flatter. It might look something more along the lines of this. Okay? That means that your error will be higher because the value here for standard deviation in your numerator will be larger, meaning your error number is larger. Okay? The last value, which is the square root of n. N is the number of samples in the data set. And it's in the denominator of this fraction, meaning that if n goes up, okay, or you have more samples, your error or your tolerance in this interval goes down, right? Because you have more samples, meaning the more data you have, the more confident that you're going to be that your data can fall within that, okay? It allows you to put tighter tolerances as you've accumulated more and more data. Similarly, if you have a lower number of samples, your error tolerance has to go up, right? If you only have 5 samples, is that really a good representation of your data as opposed to having 500 samples? Okay, so just think about that in your mind. If you have 500 samples, or if you take it in another way, if you've only done a task 5 times versus doing the same task 500 times, you get a lot more of a feel for what could or couldn't go wrong, and everything about how you do that task becomes a little bit more experienced, a little bit kind of tighter, right? You do things better. And that's kind of what this error value is showing, right? There's a reason they call it a confidence interval. So with each of these components, they want you to be able to come up with a more confident number as you get more data, as your standard deviation comes better, or as you change your confidence level, okay? Okay, so let's look at our first example. What you'll notice is I have 3 examples I'm going to cover specifically on this piece, confidence intervals. And I'm going to use the same set of data, but I'm going to tweak one of these values, okay? And I want to show you how the confidence interval, specifically the error, changes, okay? So let's look at our first example. For a group of 50 students surveyed, they exercised an average of 4.8 hours per week. Standard deviation in this calculation was 3.6 hours. Determine the 95% confidence interval for the mean number of hours exercised per week. So remember, our confidence interval is our mean, x bar, plus or minus our error. And our error is calculated as our z-score of, remember, half of our half of our error percentage, I should say, times our standard deviation sigma divided by the square root of the number of samples. So like I said, I'm going to provide you with this table for your test. It'll be on your formula sheet. So when we're looking here, in the question, it asks for the 95% confidence interval. So seeing the 95% confidence interval here, we go to our column with our z-score and we see it's 1.96. What we also know is our standard deviation, sigma, is 3.6 hours. Our mean, x bar, is 4.8 hours. And our total number of students surveyed, n, is equal to 50. So to solve this, we just substitute in each of these values. So we have first our error is equal to our z-score, 1.96, times sigma, which is 3.6, divided by the square root of our number of samples or students surveyed, which is 50. Okay, so if you calculate that out, you get 1, and it'll be 1 hour, remember, because we're looking at hours of exercise. So now we know we have x bar plus or minus our error. So we have that our 95% confidence interval would be 4.8 hours plus or minus 1 hour. Okay, so in other words, if we were to take this, it means that 3.8 hours, which is our minimum, 4.8 minus 1, less than whatever our sample is, x, is less than our maximum, which would be 4.8 plus 1, which is 5.8 hours. This interval gives us a 95% confidence interval, or 95% of students surveyed in this survey of 150 students, or 50 students, I mean. 95% of them, on average, would exercise between 3.8 and 5.8 hours a week. That's what the confidence interval is providing us here, okay? And like we're going to see in our next couple examples, this interval changes as we change certain variables in these equations. So in our second example, remember back to example 1. If we change the number of students surveyed to 150, remember, N was 50 in example 1. And now in example 2, N is 150. So with that, our mean and standard deviation are going to stay the same. Our mean being 4.8 hours and standard deviation being 3.6 hours. So once again, determine the 95% confidence interval for the mean number of hours exercised per week. Okay? So remember, we had our mean, x bar, plus or minus our error, and our error is equal to our z-score for whatever confidence level we're looking at, multiplied by our standard deviation by the square root of our number of samples. Okay? So our mean did not change, 4.8 hours. Our standard deviation did not change, it's 3.6 hours. But our number of samples changed to 150. Okay. I'm also asking for the same confidence level, which is 95%. If we go to our table for 95%, we get our z-score in our third column here of 1.96. So z is equal to 1.96. Sorry, 1.96. So substituting in these values, we get that our error is equal to 1.96 times our standard deviation, 3.6, divided by the square root of, in this case, 150. If we calculate this out, we get an error of 0.58 hours. Okay? So our confidence interval for 95%, x bar plus or minus our error, is equal to 4.8 plus or minus 0.58 hours. Or in other words, our minimum would be 4.8 minus 0.58, which is 4.22. Be less than the number of hours exercised, x, which is less than our maximum, 4.8 plus 0.58, which is 5.38. So our interval has shortened quite dramatically. It's went from plus or minus 1 hour in our first example to 0.58, or a little less than 60% of what we had initially. And the reason for that is because our number of samples increased. We're more confident in our data, so our confidence interval will decrease, meaning that, there's a better likelihood in this data that 95% of them is going to fall within a tighter window than our previous example. Okay? It all is coming down to more and more and more data and how good your data is. Okay? In our last example, okay, we're going to keep it at 50 students, just like example 1. And our mean remains the same at 4.8 hours. But the standard deviation changed to 1.8 hours. So now I want you to determine the 95% confidence interval for the mean number of hours exercised per week. Okay? So we're still finding a 95% confidence interval. Using the same formulas, we have our mean, x bar, plus or minus our error. And our error is equal to our z-score at the confidence level we select, times sigma, which is our standard deviation, divided by the square root of n, our number of samples. X bar in this case is 4.8 hours still, but our standard deviation has changed. Remember, it was 3.6 hours previously, and now it's 1.8 hours. Our number of samples is just like our first example, 50. And our z-score, again, we're doing a 95% confidence level. So going to our table, our z-score is equal to 1.96. Substituting in these values, we get our error is equal to 1.96 times our standard deviation, which is 1.8, divided by the square root of 50, our number of samples. And we see here that our error went down even further. It's now 0.5 hours. instead of 0.58, or 1 like our initial example. So it's actually cut it in half. What that means is we have x bar plus or minus our error. Our mean is 4.8 hours plus or minus 0.5 hours. So our range now is from 4.3 is less than x, which is less than 4.8 plus 0.5, which is 5.3. Again, an even tighter range now, right? Within 1 hour for the range, right? Between 4.3 and 5.3, you can see that 95% of our data should fall within that, all right? And the big reason for that is, again, remember, when we have standard deviation, our distribution of data, that's normal. If our standard deviation decreases, our data distribution would look something like this, meaning it's a tighter interval in between them. Tighter distribution of data. If the standard deviation is less than that, it becomes a flatter curve like this, okay, with a further distance between our distributions. Okay, that's kind of how that changes with our standard deviation. So what we've seen here, I've written all 3 of our example solutions here. So we started with the same data, but changing 1 variable at a time. Our first example was 50 students exercising, and they indicated they exercised an average of 4.8 hours per week with a standard deviation of 3.6 hours. In the first interval, okay, we had a 95% confidence interval of 4.8 plus or minus 1 hour. So that was 3.8 at our minimum to 5.8 at our maximum. If the sample size increased, remember in this case, we got 4.22 was less than x, which is less than 5.38. So that's just adding or subtracting our error. And for our third example, where we reduced the standard deviation in half, we went even lower. 4.3 is less than x is less than 5.3 because our error went down from 1 hour to 0.58 to 0.5. So what does this say? Well, remember, this is our error formula. The error for our confidence interval is our z-score times our standard deviation divided by the square root of our number of samples. So we've talked about this when I first introduced the example, but I want to give you a slide that shows you how the error will change. So our confidence intervals vary. And how is the real question? In the first instance, if we increase our sample size, the margin of error decreases. So if n goes up, our error goes down. If our number of samples goes down, our error goes up because we have less reliable data, okay, because we don't have as many samples. As the standard deviation increases, our margin of error increases, okay? So as sigma goes up, our error goes up. As sigma goes down, our error goes down. Okay, and that makes sense because the standard deviation is how data is distributed versus the mean. Okay, so if the standard deviation is small, it means that most of your data is clumped very close to that mean value, meaning that most of your results will come out close to that mean. Okay. The last item is that the larger the confidence interval is, remember, that was our z value, the larger the margin of error. Remember, as the z-score increased, or as the confidence level increased, your z-score increased. And that's because you're casting a blanket over a larger amount of data. 90% falls within versus 99% is a big difference, okay? So in this case, as our z value goes up, our error increases. Okay. So now we look at this and we say, well, what if we're trying to design a certain type of quality control? And we want to know how many data points, or in other words, samples, n, we need to be within a certain margin of error. Well, if we start with our margin of error formula, we can solve for our value of n. Okay? So my first step is I'm going to move that root of n to the right side or left side of the equation, and I do that by multiplying both sides by the square root of n. Remember, you can do anything you want to either side of these equations as long as you do the same thing to both sides. So if I multiply both sides by the square root of n, on the left-hand side, I have the root of n times e. On the right-hand side, I have the root of n in the numerator and the denominator, so they cancel. So I'm left with just the z-score times sigma. Now I want just n on one side. I'm trying to solve for n. Okay? So I need to get rid of this e. So I'm going to divide both sides by e, because that'll have an e in the numerator and the denominator on the left-hand side. So they'll cancel. And I'm left with just the root of n, which is equal to the z-score times sigma divided by our error. Our last step is to solve for n. Now remember, you can write n, when it's the square root, as n to the 1/2. Okay? Because this exponent is simply whatever exponent the value within the root sign is raised to, which in this case is nothing, so it's just 1, divided by whatever the order of the root is. And remember, if you have just a square root, then the value is 2. Okay? So you can write this as n to the 1/2. So I'm going to replace that with n to the 1/2. Okay? So if we want n by itself, we have to remove that exponent. And if you remember, if you raise something to another exponent, it's the same as multiplying the exponents. You multiply the two exponents together. Remember back to when we covered exponents. So what I'm going to do is I'm going to square both sides. Because on the left-hand side, what I'm going to be left with is n to the 1/2 multiplied by 2. Again, because you have an exponent raised to another exponent, so it's multiplying them together. And that's equal to z to the alpha over 2 times sigma divided by our error all squared. Now 1/2 times 2 is 1, so these will cancel each other. And what we're left with is our final formula, okay, which is n is equal to our z-score times sigma divided by our error all squared, okay? And you're going to see that as you try and reduce your error, you need more samples to reduce it, right? Remember, because as we increase the number of samples, our error went down. Okay, so let's look at one example where we actually use this rearranged version of the formula. A manufacturing engineer reviews watch components in the quality control department. The mean diameter was 2.6 millimeters and the standard deviation was 0.1 millimeters. If, at a 99% confidence interval, the engineer wants a maximum error of 0.05 millimeters for A and B 0.002 millimeters, determine the required number of samples for each. So we're given a lot of data here, okay? And we're trying to find the required number of samples. We're trying to find n. And if you remember, n was equal to our standard deviation times our z-score divided by our error all squared. Now in this case, we're at the 99% confidence interval, meaning our z is 2.575. That's for both A and B. Our mean, x bar, is equal to 2.6 millimeters. And our standard deviation is 0.1 millimeters. Okay? For part A, we want our maximum error to be 0.05 millimeters. So we want our error to be 0.05 millimeters. So we have all our data to solve for n now. So n is equal to our standard deviation, 0.1, times our z-score, which is 2.575, divided by our error, 0.05, and that's all squared. So if you convert this out, you'll get 26 approximately. Remember, rounding up if you have a decimal to the nearest sample. So we only need to have 26 samples to reasonably have a confidence interval of 99% to get 0.05 millimeters. But what if we want to get to a really tight tolerance level, 0.02 millimeters, or 2/1000th of a millimeter? Okay, remember, these are watchmaking components. You actually want them to be quite exact. So for B, what changes is our error becomes 0.002 millimeters. But everything else stays the same, right? We're at a 99% confidence interval. So N is equal to, instead, in this case, 0.1, our standard deviation is the same, times 2.575, again, our z-score is the same. But now it's divided by 0.002 because our error is a different value, and that's all squared. Now, if you do that, you get 16,577 samples. So what you see is how exponentially that value grew. And a lot of the reason for that is then you might start thinking, okay, why I need that many samples to get to that high of a tolerance, okay? Maybe that's obviously not good enough to have that many samples, right? Meaning that our values could kind of be all over the place up until that point. And what you might decide is, okay, maybe I need to change something in my manufacturing to reduce my standard deviation, okay? Because if my standard deviation is 0.1 millimeters, okay, maybe it needs to be a little bit tighter if I really want components within an error value of that, okay? So that's all I had for this lesson. We talked about confidence intervals. There's a few questions here for you to try in the textbook. I recommend you try them. These will be kind of, these styles of questions asking you to find the values of n or to find, the errors and stuff. Those are types of questions you'll be likely to see on your test. Okay. If you have any questions, send me a message on Teams or send me an email. Thanks, everybody.